In this video, we move on to the Agresti and Cool method for finding confidence intervals for the population proportion when it is unknown. You see, here is where the Agresti and Cool method is the winner. It is when we observe that the distribution of the sample proportion does not follow the normal distribution. In other words, we checked, as we usually do before computing the confidence intervals for the confidence interval rather for a population proportion based on sample data. We checked and we found that n times p hat times 1 minus p hat is not greater than or equal to 10. In other words, it's not at least 10. So this condition is not met, which means we cannot use the method we have used previously in order to find the confidence interval for the population proportion as we did on page 9. So back to this page. So what do we do when that condition is not met? Agresti and Co. proposed a different method that does not require that this condition be met. Rather than use p hat, they use p tilde, and they adjusted the formula here. Well, rather than read all of this to you, which you possibly might find boring, I will go ahead and show an example of how to use this and when, in particular, to use this. So let's proceed. We're told here in this example that Jane wants to estimate the proportion of students on a campus who eat cauliflower. After surveying 30 students, she finds 4 who eat cauliflower, obtain and interpret a 95% confidence interval for the population proportion of students who eat cauliflower on Jane's campus using the Agresti and Cool's method. Well, if we're going to attack this question by hand, usually what we'll first do is to compute our sample proportion, which is the point estimate of this quantity, the population proportion that we want to find. So the sample proportion, P hat, is usually x over n, and that will be 4 out of 30 who eat cauliflower. Just a side reminder, that was pulled up from this part of the question. So with that said, we have 4 over 30. This is equal to approximately 0.133. Well, we check what the value of n times p hat times 1 minus p hat is. N is the sample size, that is 30, multiplied by p hat, which is 0.133, and then 1 minus 0.133. If you compute this correctly on your calculator, you will get approximately 3.459. And there lies the issue. This is less than 10. It does not meet the condition for using the normal approximation to the binomial distribution to build the confidence interval for the population proportion. So when this happens, an alternative approach that does not require this condition to be met is the Agresti and Cool's method for computing confidence intervals for the population proportion. And rather than use p hat in this case, it uses p with a tilde. And this is defined as x plus 2 all over n plus 4. As you might observe, that is a slight adjustment to the initial formula for p hat. So in this case, it will be 4 rather than 4, it will be 4 plus 2. And on the bottom, it will be 30 plus 4. In particular, these 2 and 4 are fixed constants. Think about them like pi in pi r squared. So they're fixed constant in this formula. They don't change. So this will be 6 divided by 34, which is 0.176. Once we get this value, the next thing we need to get, in order to use the formula, as you might observe, we have gotten p tilde. We need to get z of alpha over 2. So what do? Take note, in this case, you will need to know how to do this by hand. StatCrunch is not very effective at getting the correct answer in this case. So please do pay more than usual attention as we walk through this problem. So I'm going to illustrate the normal distribution there. And the interest, I don't need to draw this, I need to find, according to the question, a 95% confidence interval. That means I am going to center 95% in the middle to construct a range or interval. So 95%, 0.95. Then I need to find this z of alpha over 2 value here. How do I do that? I'll go to StatCrunch. So here we are in StatCrunch. I'll go to Stats, I'll go to Calculators, then I'll go to the normal calculator. And here under the normal calculator, I'll drag and slide this way. And I'm interested in between. The size of this shaded area, based on the template I have ready, is 95% confidence interval. So I want 0.95, as we have illustrated earlier, here. So you have 0.95, and I'm going to leave these two parts blank. Leave 0 and 1 as is, and compute. So I have 1.96 right there, very close to 2. So as it stands, I can go back. This is equal to 1.96. Then the next part I need, according to the formula, is the standard error. So I am going to find that standard error. So this is the standard error of p tilde, and that is the square root of p tilde, 1 minus p tilde, all over n plus 4. So this will be, I need to plug in the value of p tilde, which is 0.176, multiplied by, so if p tilde is 0.176, you have 1 minus 0.176 divided by, on the bottom, n is 30. So 30 plus 4. And so let me take this away so that we can easily see this. And this will be approximately equal to 0.065310. Please, when you complete what you have on the square root, do not forget, finally, to take the square root of that answer. So with this set, I now have all the pieces I need. So using the Agresti method, Agresti-Coles method, a 95% confidence interval for P, the proportion of students who eat cauliflower on Jane's campus, is given by P tilde plus or minus Z of alpha over 2 multiplied by the standard error of P tilde. Oh, excuse me. I'm going to just write standard error of P tilde. All right, so what is the value of P tilde? It is 0.176. We saw that here. Plus or minus, what is the value of Z of alpha over 2? It is 1.96. What is the value of the standard error? It is 0.065310. Following PEMDAS, I'm going to need to multiply first. 1.96 times 0.065310, you have 0.128. And so, to get the confidence interval, it is 0.176 minus 0.128 on the lower end, and 0.176 plus 0.128 on the upper end. This gives 0.048 to 3 decimal places to 0.304. This is the required 95% confidence interval for the population proportion using the Agresti and Coles method. So, with that said, we are done with that part of that question. Then we have the part that says we should use technology. I wanted to point out that you should do not use StatCrunch in this case. You will need to compute the single problem or whatever problems you have on Agresti and Coles method using hand calculations. So please note that. Okay, with that said, we proceed to what to do or what formula should we use when we need to find the sample size that we need to construct a 1 minus alpha 100% confidence interval for the population proportion. This is where this whole idea stems from. If you look at past problems, we have been given n equals 30. For example, this is the sample of 30 students. In previous problems we have looked at again, you observe that we're already given the sample size, n equals 1,000. Again, just to illustrate again, we're given n equals 2,318. What if n was unknown? What if we don't know how many sampling units to include in our sample in order to construct a confidence interval for an unknown population proportion? How do we go about it? That question is what we intend to answer starting on page 13. So let's begin. The good news is that we have a ready-made formula that helps us only when you're trying to find an unknown sample size, only when you're trying to estimate the population proportion. Note, this formula should not be used when you're trying to estimate population mean. This formula should not be used. This should only be used when you're trying to find the sample size when you're trying to estimate the population proportion. To illustrate how to use this formula, let's take the first example. So in this example, we're told that a television sports commentator wants to estimate the proportion of citizens who follow professional football. We have to complete parts A through C. The first note to make here is that we're trying to estimate a proportion. So we proceed to question A, or part A of the question. What sample size should be obtained if he wants to be within 3 percentage points with 95% confidence if he uses an estimate of 54% obtained from a poll? So, in other words, this 54% is what we call a prior estimate. That prior estimate is your P-at in this formula. That is 0.54. So as it stands, we have our P-at. The next thing we need is Z. To find our Z, we need our normal distribution and the confidence level, which is 95%, 0.95. And we need this value right here. So we go to Start Crunch. And interestingly, we just did that. So when it is 0.95, the value we're searching for is 1.96. So I take that back. You have 1.96. Take that back to my working board. And then the next thing is, so I have Z, I have P-at already, and I need the margin of error. The margin of error, or E, if you would, we're told that we want this to be within 3 percentage points. That's our wiggle room. So manage, we have 3, but this is 3 percentage, so 0.03. So as it stands, we are ready to go. So plug in our value of n is P-at times 1 minus P-at multiplied by Z divided by margin of error, all square. Please do not forget the square. This is a common error. So this is equal to 0.54 multiplied by 1 minus 0.54. 1 minus 0.54 is the same as 0.46. Then our Z is 1.96 divided by 0.03 all square. So if you compute this correctly, let me separate the given from what we're computing. This will be equal to approximately 1060.2816. All right, it is important at this point to mention that you must always round up in this case, never round down. Even though this is 2, we're going to round up to the next integer. So we round up, and that will be equal to 1061. So this will be the sample size. Then we proceed to question B. what sample size should be obtained if he wants to be within 3 percentage points with 95% confidence if he does not use any prior estimates. So if there are no prior estimates, under that condition, no prior estimates, we always set P-hat to 50-50 chance. So that will be 0.50. Please take note, this should only be used when there is no prior estimate from a previous poll or survey. So we still have the margin of error is still 3 percentage points. We're still looking at 95% confidence interval. So that means our Z is still 1.96. That is what this 95% tells us. The margin of error is 3%, which is 0.03. So with this given, we use the formula yet again. N equals P hat, 1 minus P hat, then Z all over margin of error, all square. That will be 0.5 multiplied by 1 minus 0.5, which will give exactly 0.5 yet again. Then Z is 1.96 divided by the margin of error, all square. This will be equal to 1067.1111. That continues. So again, you round up, which is 1068. This is the sample size. At this point, we proceed to part C. Why are the results from part A and part B so close, from 1061 to 1068? If we observe closely how we obtained the answer in part A and in part B, we will observe that the calculations that led to that solution have something in common. They both have the highlighted part on your screen as common. That is, they both have 1.96 all over 0.03 all square. Where there is a difference comes from whether you have a prior estimate or you don't have a prior estimate. And so you observe that the answer for this value, that is 0.54 times 0.46, is very close to 0.5 multiplied by 0.5, which is, of course, this is 0.25. So the results are close because this multiplication is very close to 0.25. With that said, we proceed to the next example. In preparing a report on the economy, we need to estimate the percentage of businesses that plan to hire additional employees in the next 60 days. So again, note that this is about making an estimation for a proportion of businesses that plan to hire additional employees in the next 60 days. Question A. How many randomly selected employers must be in contact, or must we contact, in order to create an estimate in which we are 98% confident with a margin of error of 5%? Since this question is about estimating a proportion, and we're trying to find a sample size, so we're good to use this formula. And you have Z all over the margin of error all square. This will be equal to 0.5, since we do not have a prior estimate, 1 minus 0.5. What you observe is that since we are getting 0.5 here, this would be the same thing as what we had earlier in the last example. 0.5 times 0.5, this will give us 0.25 for the first two values. In fact, I'll just keep them that way so that there are no confusion. And then our Z is currently unknown. So we need to find Z. So what is Z? Let's take a quick step out. So we want a 98% confidence interval. That'll be 0.98, right in the middle. And I need to find the Z value here. So I'll go back to Start Crunch, and I'll alter this. I'll change it to 0.98 and compute. This is 2.3263. So I'll take that back. This is 2.3263. That is the value of my Z, 2.3263 divided by the margin of error. The margin of error is 5%, so that is that. So we have 0.5 times 0.5, that will be 0.25. You observe that these would always appear, this 0.25 will always appear whenever we do not have a prior estimate. So multiplied by 2.3263 divided by 0.05. This will be equal to, before we conclude on that, we might observe that that popular error almost popped up here. So there should be a square there. So if you compute all of this, this should be approximately equal to 541.0276. And so we round up to approximately 542 employers should be contacted. Then the next example, we use the same formula. Again, Z all over margin of error all square. The only thing that is changing from 5% to 3% is the margin of error. And so we have every other piece staying the same. 0.5, 0.5, I will get 0.25. So I'm just going to put that back here. My Z, I'm still computing a 98% confidence interval. So my Z will still remain as 2.3263. The only thing that is changing is the margin of error to 3%, all square. Okay, so with that said, what would we get? In this case, we'll get approximately 13525.69. If we round up, that'll be approximately 13,526 employers. What do you think? Just dropping the margin of error by 2% increases our workload from 542 employers to contact to 13,526 employers. That is quite a significant stretch there. Then question C, why might it not be worth the effort to try to get an interval with a margin of error of 1%? Again, using the same formula, we are trying to experiment with what if we wanted to drop the margin of error to 1%. So every other item here remains the same. That is, you still have 0.25. Then you have 2.3263 divided by, rather than margin of error being 0.03, it is now 1%, all square. This will give approximately, oops, I just realized I had an error earlier. Sorry about that. This value should be approximately, I had the answer for this guy, I put it up here. That was my bad. So let's adjust that again. The answer for this should be approximately 1502.85444. That will be rounded up approximately 1,503 employers. Apologize about that. And then for the last one, that was the answer I had earlier. This will be approximately 13,525.69. That will be rounded up. That will be 13,526 employers. Well, going from 5%, which required 542, to 1,503 employers, to 13,526 employers, it is clear here that it might not be worth the effort trying to get down to 1% because it's going to be extremely resource intensive to be able to contact all 13,526 employers. So it might not be worth the effort. So with that, we come to the end of the consideration of how to compute and interpret and make everyday applications of the concept of confidence intervals for population proportions.